Welcome! In this session, we'll dive into problem number 937, reorder data in log files. Together, we'll explore the problem, analyze the requirements, and work through an efficient solution. Let's get started. In this problem, you are provided with an array of logs, where each log is a string consisting of an alphanumeric identifier followed by either a sequence of words or digits. These logs are categorized into two types, letter logs and digit logs. If the portion after the identifier contains only lowercase English letters, it is classified as a letter log. On the other hand, if it contains only digits, it is considered a digit log. The task is to reorder these logs based on certain rules. First, all the letter logs should appear before the digit logs. Second, the letter logs must be sorted lexicographically by their content. If there is a tie in content, they should be sorted by their identifiers. Finally, the digit logs should maintain their original relative order. Once reordered, the function should return the resulting array of logs. The output of the function is also an array of strings, which represents the reordered logs. Let's look at an example to better understand the problem. Suppose the input array is dig18151, let1 art_can, dig236, let2 own_kit dig, let3 art0. Here, there are three letter logs, namely let1 art_can, let2 own_kit dig, and let3 art0, and two digit logs, dig18151 and dig236. For the letter logs, we focus only on their contents for sorting. The contents are art_can, own_kit dig, and art0. These are sorted lexicographically, so art_can comes first, followed by art0, and then own_kit dig. The digit logs remain in their original order. Therefore, the final output is let1 art_can, let3 art0, let2 own_kit dig, dig18151, dig236. To break this down further, let1 art_can is placed before let3 art0 because art_can comes before art0 lexicographically. Similarly, let3 art0 comes before let2 own_kit dig because art0 is smaller than own_kit dig. The digit logs, dig18151 and dig236, are left untouched and appended to the result after all the letter logs. Now, let's look at another example. If the input is A19231, G1 act car, Zo447, AB1 off key dog, A8 act zoo, there are three letter logs, G1 act car, A8 act zoo, and AB1 off key dog. Their contents, act car, act zoo, and off key dog, are sorted lexicographically, so G1 act car comes first, followed by A8 act zoo, and then AB1 off key dog. The digit logs, A19231 and Zo447, retain their original order and appear at the end. The final output is G1 act car, A8 act zoo, AB1 off key dog, A19231, Zo447. There are a few constraints and edge cases to consider. The length of the logs array can range from 1 to 10,000, and each log string will be at least 3 characters and at most 100 characters long. Each log is guaranteed to have an identifier and at least one word or number after it, separated by a single space. For edge cases, if all logs are digit logs, the output will be the same as the input since digit logs maintain their relative order. For instance, if the input is dig18151, dig236, the output will remain unchanged as dig18151, dig236. If all logs are letter logs with identical content, they will be sorted by their identifiers. For example, given let2 art_can, let1 art_can, the output will be let1 art_can, let2 art_can. Finally, in cases where letter logs have ties in content, the identifiers are used as the tiebreaker, and digit logs are still appended at the end. For example, with input A1 act car, B2 act car, C3123, the output will be A1 act car, B2 act car, C3123. To tackle the problem of reordering logs, two main approaches come to mind. The first is a brute force approach, where we sort the logs using a custom comparator. The intuition here is straightforward, since the goal is to reorder logs, sorting them by specific rules can achieve the desired result. The challenge lies in distinguishing between letter logs and digit logs, as they are treated differently. The process involves parsing each log to classify it based on its content, whether it starts with letters or digits. For letter logs, we sort lexicographically by their content, and in the case of a tie, the identifier acts as a tiebreaker. Digit logs, on the other hand, retain their original order and are simply appended after the sorted letter logs. While this approach is conceptually simple, implementing the sorting logic manually can be verbose and potentially inefficient, especially for large inputs. The computational cost of this approach is O(m *n log n, where n is the number of logs and m is the average length of each log. An optimized alternative involves leveraging Python's built-in sort function, which simplifies the process significantly. Here, we use a custom key function to define sorting priorities instead of manually comparing logs. This approach reduces code complexity and takes advantage of Python's highly optimized sort algorithm. Using the optimized approach, we define a key function to handle the sorting priorities. For letter logs, the key function returns a tuple 0 content identifier. The 0 ensures letter logs are prioritized over digit logs, while the content and identifier determine the order within letter logs. For digit logs, the key function returns a tuple 1, ensuring they are placed after all letter logs while retaining their relative order due to Python's stable sorting. By applying this key function, we can sort the logs in a concise and efficient manner. This approach offers several advantages. It is concise, leveraging Python's optimized algorithms, and avoids the verbosity of manual comparison logic. However, it does require an understanding of tuple-based sorting behaviors in Python. Despite this, the complexity remains O(m *n log n, the same as the brute force approach. The difference is that the key function reduces implementation overhead and makes the code cleaner and easier to maintain. The chosen strategy is to use the optimized approach with the key function. This decision is based on several key observations. First, letter logs take priority and are sorted lexicographically, with ties broken by their identifiers. Second, digit logs maintain their relative order and appear after all letter logs. Finally, Python's stable sorting ensures the relative order of digit logs is preserved automatically. The real breakthrough came from realizing that all sorting rules could be encoded directly into the key function, eliminating the need for manual comparisons. This approach strikes a good balance between clarity and efficiency, avoiding the pitfalls of verbose code while leveraging Python's robust capabilities. The final complexity of our solution reflects the sorting process. The time complexity is O(m *n log n, where n is the number of logs and m is the average length of a log. This covers the cost of sorting the logs using the key function. The space complexity is O(m), which accounts for the intermediate data used during the sorting process. Here's the Python implementation of the solution. We define a function reorder log files that takes a list of logs as input. Inside it, a helper function log_key determines the sorting priorities. For each log, we split it into an identifier and content. If the content starts with a letter, we return a tuple 0 content identifier to prioritize it. If it starts with a digit, we simply return 1 to ensure digit logs are placed at the end. Finally, we use Python sorted function with this key function to reorder the logs and return the result. This implementation is concise, efficient, and directly aligns with the problem's requirements, making it an effective solution to reorder data in log files. The problem requires us to reorder an array of logs, where each log consists of a unique identifier followed by its content. The content can either be letters, making it a letter log, or digits, making it a digit log. Our goal is to reorder these logs based on specific rules. First, all letter logs must appear before digit logs. Then, the letter logs need to be sorted lexicographically by their content. If two letter logs have the same content, they should be sorted by their identifiers. Lastly, digit logs must maintain their original order and simply follow the sorted letter logs. To achieve this, we start by parsing the problem. The task involves identifying and separating the logs into letter logs and digit logs. Sorting applies only to letter logs, and since digit logs need to maintain their original order, we require stable sorting. To determine the type of log, we can examine the first character of the content after the identifier. If it's a digit log, otherwise, it's a letter log. With this understanding, we can move on to designing a custom comparator for sorting. To sort the letter logs, we need a custom comparator. The rules for this comparator require us to first compare the letter log contents lexicographically. If two logs have identical content, we then compare their identifiers lexicographically to determine their order. Once the comparator is defined, the algorithm can be implemented in 3 key steps. First, we partition the logs into 2 separate lists, one for letter logs and one for digit logs. We can achieve this by splitting each log into its identifier and content using Python's strsplit method. By checking the first character of the content, we classify the log as either a letter log or a digit log. Next, we sort the letter logs using the custom comparator, which can be implemented using Python's sort function and a key function. Finally, we combine the results by appending the digit logs, in their original order, to the sorted letter logs. This ensures that the final output satisfies all the problem's requirements. Key insights include the importance of stable sorting for preserving the order of digit logs, the use of lexicographical sorting for the letter logs, and leveraging Python's efficient sorting algorithms to achieve an overall complexity of O(n) log n. The algorithm uses simple yet effective data structures to achieve the desired outcome. The input logs are stored as a list of strings, which allows for efficient partitioning and manipulation. For the sorting process, each letter log can be represented as a tuple containing the content and the identifier. This structure simplifies the sorting logic, as the tuple format matches the rules of our custom comparator. Let's look at the code implementation. First, we define a function reorder_logs that takes the input list of logs. We initialize 2 lists, one for letter logs and another for digit logs. While iterating through each log, we split it into its identifier and content. If the first character of the content is a digit, we add the log to the digit logs list. Otherwise, we append a tuple of the content and identifier to the letter logs list. Next, we sort the letter logs using a lambda function as the key, which sorts by content first and then by identifier. Finally, we merge the sorted letter logs with the digit logs, reconstructing the original log format for the letter logs. This implementation neatly integrates partitioning, sorting, and merging, adhering to the problem's constraints and ensuring correctness. When considering edge cases, the algorithm remains robust and handles various scenarios effectively. For example, if all logs are letter logs, the algorithm simply sorts them lexicographically. If all logs are digit logs, they are returned in their original order, as no sorting is applied to digit logs. For an empty input, the algorithm correctly returns an empty list. In cases with a mix of letter logs and digit logs, the partitioning step ensures that each type of log is handled appropriately. The complexity analysis further highlights the efficiency of the solution. The time complexity is O(n) log n, driven by the sorting of letter logs, while the partitioning step operates in O(n). The space complexity is O(n), as we store the partition logs separately. Let's walk through an example to illustrate the execution. Given the input logs, we first partition them into letter logs and digit logs. For instance, logs like G1 act car and A8 act zoo are classified as letter logs, while logs like A19231 are digit logs. This partitioning step sets the stage for the sorting and merging processes. After partitioning, we proceed to sort the letter logs. Using the custom comparator, the logs are sorted first by their content. For example, G1 act car comes before A8 act zoo because act car is lexicographically smaller than act zoo. If 2 logs share the same content, such as A8 act zoo and A1 act zoo, the identifiers are compared to determine the order. Once sorted, the letter logs are combined with the digit logs, which are appended in their original order. The final output is a reordered list of logs that satisfies all the problem's requirements. Key optimizations in the algorithm include using tuples for sorting, which simplifies the comparator logic, and partitioning the logs upfront to minimize the sorting scope. Additionally, leveraging Python's timsort ensures that the sorting process is both efficient and stable. This careful design guarantees that the solution is not only correct but also optimized for performance, making it well suited for large inputs. This Python implementation solves LeetCode problem 937, reorder data in log files, by processing an input list of logs and reordering them according to the specified rules. The solution consists of the following steps. 1. Define a helper function. The get_sort_key helper function extracts the content and identifier of a log and returns a tuple, content, identifier. This tuple is used as the sorting key for letter logs, ensuring they are sorted lexicographically by content. If 2 logs have identical content, they are further sorted by their identifier. 2. Separate logs into two groups. The algorithm initializes two lists, letter_logs 4 logs with alphabetic content and digit_logs 4 logs with numeric content. It iterates through the input list logs, checking if a log is a digit log by examining the first character of its content, after the identifier. Letter logs are added to letter_logs, while digit logs are added to digit_logs. 3. Sort letter logs. The letter_logs list is sorted using Python's built-in sort method, with the get_sort_key function as the sorting key. This ensures the logs are ordered according to the problem's requirements for letter logs. 4. Concatenate the results. Finally, the letter_logs and digit_logs lists are concatenated, with letter_logs appearing first, followed by digit_logs. The order of digit_logs is preserved as required by the problem. This solution is efficient, leveraging Python's timsort algorithm for sorting, which operates in n log n time complexity for the letter_logs list. The separation of logs into two groups is done in n time, where n is the total number of logs. Overall, the solution is well optimized and adheres to the problem's constraints. The implementation handles edge cases, such as empty input lists, logs with identical content, and logs with mixed letter and digit characters. By systematically separating, sorting, and combining the logs, the solution guarantees correctness and clarity. Here, we start by importing the necessary Java utilities. The method reorder log files takes an array of log strings as input and aims to reorder them based on the problem's requirements. To begin, we separate the logs into two categories, letter logs and digit logs. We use two lists, letter logs and digit logs, to store these categories respectively. We then iterate through each log in the input array. Each log is split into two parts using split, 2, which divides the log into an identifier and the rest of the content. If the first character of the content is a digit, the log is classified as a digit log and added to digit logs. Otherwise, it is treated as a letter log and added to letter logs. Next, we focus on sorting the letter logs. To achieve this, we use a custom comparator with the collections.sort method. The comparison is done first by the content of the logs. If two logs have the same content, then their identifiers are compared to determine the order. This ensures that the letter logs are sorted lexicographically by content, with ties broken by their identifiers. After sorting the letter logs, the next step is to combine the results. We create a new list called result and initialize it with the sorted letter logs. Then, we append all the digit logs to it in their original order, as the problem specifies that the digit logs should maintain their relative positions. Finally, the method returns this combined list as the result. This approach ensures that the logs are reordered correctly, with the letter logs appearing first, sorted as required, followed by the digit logs in their original order. This completes the implementation, and the solution adheres to the constraints and requirements of the problem. Here, we are looking at an example where the input contains a mix of letter logs and digit logs. The logs are initially stored in a list, and our task begins by initializing two separate lists, one for letter logs and another for digit logs. We then iterate through the input logs one by one. For the first log, let1 art can, the content after the identifier is art, which is not numeric. So, it is identified as a letter log and added to the letter_logs list. Next, for dig18151, the content begins with 8, which is a digit, so it is classified as a digit log and added to digit_logs. We continue this process for the remaining logs. Let2onKitDig is recognized as a letter log and added to the letter_logs, and let3art0 is also identified as a letter log, completing the separation step. At this point, the letter_logs list contains 3 entries, and the digit_logs list contains 1. Now that we have separated the logs, the next step is to sort the letter logs. We use a custom sorting key that splits each log into two parts, the content and the identifier. This allows us to sort the logs first by their content lexicographically, and in the case of ties, by their identifier. For example, let1 artcan is split into artcan, let1, let2 onKitDig becomes onKitDig, let2, and let3 art0 is split into art0, let3. After applying this sorting logic, we get the sorted order of letter logs as let1 artcan, let3 art0, and let 2 own kit dig. Finally, we concatenate the sorted letter underscore logs with the unsorted digit underscore logs. The resulting list is let 1 art can, let 3 art 0, let 2 own kit dig, followed by dig 18151. This gives us the final output for this example. In this example, we are given logs that consist only of digit logs. As before, we start by initializing 2 empty lists, letter underscore logs and digit underscore logs. When we process each log, we find that all of them are digit logs because their content after the identifier is numeric. Therefore, the digit underscore logs list ends up containing all the logs from the input, while the letter underscore logs list remains empty. Since there are no letter logs, there is no need for sorting. The digit underscore logs retain their original order, which simplifies the combining step. With no letter logs present, the final result for this example is simply the unsorted digit underscore logs. The output consists of the logs dig 136, dig 2432, and dig 310, in the same order as they appeared in the input. This demonstrates how digit logs are always preserved in their original sequence, regardless of the presence of other types of logs. Next, we will examine an example with only letter logs to see how they are handled when no digit logs are present. In this example, all the logs are letter logs. As before, we initialize the letter underscore logs and digit underscore logs lists. Since the content after the identifier in each log is alphabetic, all the logs are classified as letter logs and added to the letter underscore logs list. The digit underscore logs list remains empty. Now, we proceed to sort the letter underscore logs using the custom sorting key. Each log is split into its content and identifier, such as let 1 abcdef into abcdef, let 1, let 2 xyzabc into xyzabc, let 2, and let 3 abcdef into abcdef, let 3. Sorting these logs by content first, and by identifier in case of ties, results in the ordered let 1 abcdef, let 3 abcdef, and let 2 xyzabc. Finally, since there are no digit logs, the final result is the sorted letter underscore logs list. To summarize, the solution involves separating the logs into letter logs and digit logs. Letter logs are sorted lexicographically by their content, and in the case of ties, by their identifier. Digit logs retain their original order and are appended to the end of the result. The final output is always a concatenation of the sorted letter logs followed by the digit logs. This approach ensures that the logs are rearranged in the desired order efficiently while respecting the problem's constraints. To analyze the time complexity of the solution, we begin by examining the process of separating letter logs from digit logs. In this step, the solution iterates over the entire list of logs. For each individual log, it splits the string at the first space to determine whether the content starts with a digit or not. Now, splitting a string takes time proportional to its length, which we denote as m, the average length of a log. Since this operation is repeated for all n logs in the input list, the total time complexity for this step becomes O, n asterisk m. This covers the initial log separation step. Now, let's focus on sorting the letter logs. The letter underscore logs list is sorted using a custom key function. This key function splits each log into two components, the identifier and the content. For the k letter logs in the list, the key function performs a string split for each log, which takes O, m the time. Therefore, generating the sorting keys for all k letter logs requires O, k asterisk m. Next, the sorting algorithm itself, which is typically timsort, operates with a time complexity of O, k asterisk log, k. Since the sorting relies on comparing tuples, content, identifier, each comparison takes O, 1, time. Combining these, the total time complexity for sorting the letter logs is O, k asterisk m plus k asterisk log, k. Finally, concatenating the sorted letter logs with the digit logs involves iterating through the entire list once, resulting in an O, n operation. This completes the breakdown of the individual steps. When we combine the time complexities of all the steps, we get the overall time complexity of the solution. The separation of logs contributes O, n asterisk m, sorting the letter logs adds O, k asterisk m plus k asterisk log, k, and concatenation is O, n. Since the number of letter logs, k, is always less than or equal to the total number of logs, n, we simplify the overall complexity to O, n asterisk m plus n asterisk log, n. Here, the n*m term accounts for splitting and processing the strings, while the n*log n term arises from sorting. This is the dominant term for the solution. Now let's evaluate the space complexity, starting with the auxiliary space used for separating the logs. The solution creates two separate lists, letter_logs and digit_logs, to store the respective types of logs. Together, these lists require n space, where n is the total number of logs. Next, the sorting of letter_logs requires additional space for comparisons. The sorting algorithm, timsort, uses k auxiliary space in the worst case, where k is the number of letter logs. Additionally, the key function temporarily generates tuples in the form content identifier for each letter log, which also requires k space. Combining these contributions, the overall space complexity of the solution is n plus k. Since k is at most n, this simplifies to n. To understand the advantages of the current solution, let's compare it with a naive approach. In a naive approach, all logs could be sorted together without separating digit logs and letter logs. This would require processing all n logs using a custom key, resulting in a time complexity of n*m plus n*log n. However, since digit logs don't need sorting, this approach introduces unnecessary computation. In contrast, the optimized solution separates digit logs from letter logs. By focusing the sorting only on letter logs, the solution avoids redundant operations, making it more efficient. The complexity remains n*m plus n*log n, but the computational overhead is lower in practice. Additionally, the best-case scenario for the current solution occurs when all logs are digit logs, requiring only n*m time. In average or worst cases, with mixed or all letter logs, the complexity is n*m plus n*log n. This makes the solution robust across all inputs. Lastly, let's confirm the overall complexity mathematically. Splitting each log to separate letter logs and digit logs contributes n*m. Sorting the letter logs adds k*m plus k*log k. Since the total number of logs is n, and k is at most n, we can replace k with n in the worst case. This gives a total complexity of n*m plus n*log n. Thus, the solution is bounded by this expression, which effectively captures the combined costs of splitting, sorting, and concatenating the logs. When solving this problem, there are several common mistakes to watch out for. First, it's easy to overlook edge cases, like when the input is empty, all the logs are digit logs, or when multiple letter logs have identical content. These scenarios can lead to incorrect results, so it's crucial to test your solution against a variety of edge cases. Another common issue is implementing the custom comparator incorrectly. For example, mixing up the logic for ascending versus descending order can cause the sorting to behave unexpectedly. Always double-check your custom sort logic and validate it with diverse inputs. Additionally, sorting inefficiencies can arise if you don't make use of stable sorting. Stable sorting is helpful because it preserves the relative order of equivalent elements, which simplifies multi-criteria sorting. Misidentifying logs is another potential pitfall. Logs with mixed characters can make it tricky to distinguish between digit logs and letter logs. To avoid this, ensure your validation logic is robust. Lastly, hard-coding assumptions about the log structure, like assuming a specific number of spaces, can cause your solution to fail if the input format changes. A more flexible approach is always better in these situations. This problem is a great opportunity to demonstrate your knowledge of sorting algorithms. One key insight is the emphasis on stable sorting and custom comparators. Focus on writing clear and correct logic rather than trying to overcomplicate things with clever tricks. For optimization, you can rely on Python sorted, or Java's arrays.sort, both of which support custom comparators or lambdas and are optimized for performance. Recognizing that this is a variation of multi-key sorting is also beneficial, as mastering this pattern can help you tackle other problems that involve sorting or ordering based on multiple criteria. In an interview setting, it's important to clearly explain your reasoning, particularly why you prioritize letter logs over digit logs. This shows you understand the problem requirements and can justify your approach logically. Beyond this specific problem, There are other related challenges that share similar principles, such as grouping anagrams, implementing custom sorting logic, or sorting linked lists under constraints. Practicing these problems can further solidify your understanding of sorting patterns. There are several approaches you can take to solve this problem, each with its own trade-offs. A brute force approach involves manually comparing logs pair by pair. While this method may seem intuitive, it's highly inefficient, with a time complexity of n squared, making it impractical for larger inputs. A more efficient option is to use optimized sorting with a custom comparator. This approach leverages built-in sorting algorithms and achieves a time complexity of n log n. It's concise and effective, especially when implemented with a clear comparator. Another approach is bucket-based sorting, where you separate the logs into letter logs and digit logs, sort the letter logs using a custom comparator, and then combine the results. This method provides clarity by isolating different concerns but requires additional space for the buckets. Finally, a hybrid approach combines the efficiency of bucket-based sorting with the simplicity of built-in sorting, allowing you to balance clarity and performance. This flexibility is particularly useful in interviews, as it showcases your ability to adapt and optimize based on the problem requirements. Great job! To wrap up, we reviewed the problem, discussed a custom sorting solution, and summarized key concepts. Keep practicing sorting and string manipulation problems to strengthen your skills. Thanks for joining, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!